Hello everybody, welcome back to the channel. So today we're going to talk about a couple of topics. The first one is the energy analysis of the coupled inductor. Let's see how the energy stored in the inductor is about, and there's possible way of minimizing the energy stored in the inductor. And the second topic, the ideal transformer, which covers the basics of the voltage and current ratios, and also the equivalent impedance due to the transformer. So today, the content corresponds to two sections in the text. So each video clip might be a little bit long. I'm planning for 3 video clips, and hopefully we can get through that smoothly. And let's start with the energy analysis for the coupled inductor. Remember the coupled inductor we had, the two currents may create a flux then add to each other, and also they could subtract to each other depending on the dotted sign convention we talked about loss in the last lecture. And if you remember, for the first case we would have so the voltage is going to be equal L1 self-inductance times di1 dt plus or minus plus for this case and a minus for this case, because these both current go into dotted terminals. We're going to have plus M, which is the mutual inductance di2 dt, and V2 is going to be equal plus minus M di1 dt plus L2 di2 dt. And if we look at the power into the inductor, so the power is going to be power into the inductor, that's P is a function of time, since all the variables I and V's are a function of time, and P is going to be equal to V1 times I1 plus V2 times I2. And if I substitute this V2 and V2 and V1 into the P here, and then the PT should be equal to, I think I can move up a little bit. PT should be equal to V1, which is L1 I1. So I'm substituting V1 into the first term, and I multiply them out. I have a di1 dt plus minus M times I1 di2 dt. Right, and then plus minus M, so I'm substituting this one into here, so I'm multiplying I2 di1 dt and plus L sub 2 I sub 2 di sub 2 dt. And alternatively, I can write this, I can take the derivative and the whole thing, and then I get half L1 I1 squared plus minus M I1 times I2 plus half Li2 squared, right? And since we know the energy, the power is the derivative of the energy, so the energy stored, the energy storage inside the coupled inductor is going to be, let's use W. Wt is going to be equal, what's in the brackets, half L1 I1 squared plus minus M I1 I2 plus half L2 L sub 2 here and I sub 2 squared. Right, so that's the energy. And let's look at the energy. And if let's see, if I1 is given, that means you can't change this anymore, and still maybe time varying. And then and I2 can minimize the Wt if we take a partial derivative with Wt with respect to I2, partial I2, and then we get, so if we take a partial derivative, and the first term will be gone, and you get a plus minus m times I1 and plus L2 times I2. Right, and if this should be equal to 0. If this satisfies this, or I2 is equal minus or plus m times m over L2 and times I1. And this is a condition that will minimize the energy stored in the inside the coupled inductor. And under this condition, the minimum energy should be equal to W mean is going to be equal to, let's see, we substitute this I2 into the W, and we will get half L1 I1 square, and minus plus times plus minus, so we always get a minus m square over L2, and then I replace I2 by this, and so I get I1 square, right? And also I have plus the half so half L2 times m square over L2 square, which is m square over L2, because L2 be canceling one of the L2 on the denominator here, and then I1 square. I think that's it. And since this should be equal to half L1 I1 square minus half m, because these two terms are the same, and minus 1 plus half, that's negative half m square over L2 I1 square, right? And if you put them in the, let's see, if we put them in a common denominator, I have 2L2, and for the numerator, I have L1 L2 minus m square times I1 square. And this whole thing should be greater than 0, right? Because that's the energy. And we'll see. And let's define a variable called the coupling coefficient. Let the coupling coefficient K defined as m over square root of L1 over L2. And if we define this parameter here, and what we can get is, let's see, what we can get is, we can change the omega mean. The omega mean is going to be equal half L1 times 1 minus m square over L1 L2 times I1 square. And if you recognize this should be equal k square, so therefore the half of L1 times 1 minus k square and I1 square. So this is the minimum energy if we have the I1 is fixed, is given, and I2 is allowed to vary. And based on this, we should be able to see the k should be greater than 0, less than 1, right? So when the k equal to 1, that means perfect coupling. And as we will see, the ideal transformer perfect coupling means there is no leakage, the flux. So all the flux are going to be linking the other winding, and that's for the k equal to 0. That means there are no coupling at all, right? So that's 0 coupling. So this is the case for if the I1 is given and I2 can minimize this. Alternatively, if you have let's see, we do, let's see if we can have, let's see if, let me change the color. I don't know if they will save a little bit of time. Let's see if I change the color to red. Let's see if I2 is given, and I1 can change this, right? And in that one, I will have partial omega t, partial w, partial I1, that's going to be equal to L1 times I1 plus minus m times I2. And the condition for this one going to be equal to I1 is going to be equal to minus plus m times m over L2, m over L1, not L2, L1 times I2, right? And the omega mean, if you do the similar, the omega mean, the W mean, that should be equal to, you substitute the I1 into the original equation, that should give you something like half L1, L2 minus m squared times I1 squared, I2 squared. And if you do, so that's the, if you use the covenant coefficient, that should give you half L2 1 minus k squared I2 squared, right? So that's the two scenarios. I'm not going to go through the detailed in the Google Colab notes in this for this lecture. There is more detailed derivation there. Okay, let's look at an example and see if we can make sense out of these. And let me change the color back to blue. So I have a couple of inductor for both current flow into the dotted terminals. That's the case we went through in detail, and we have the current I1 given, and we have the inductance, the self-inductance and mutual inductance are given. We're trying to find the covenant coefficient. The covenant coefficient in this one here, k is going to be equal m over, it's just a simple algebra, L2, that's equal to, I have this calculated before, that's 0.73. This is for the first one. And for the second one, the kernel I2, that's going to be minimize the energy storage. And we know the I2 should be equal minus, because that's the they both go into the dotted terminal, right? And that's minus m over L over L2 times I1. And I also calculate this one here. That should be minus 1.6 sine 100t. And the minimum energy storage, the minimum energy storage, the W mean, the W mean is half L1 1 minus k squared times I1 squared. And I calculate this in the final form. That should be 0.0056 times 1 plus cosine 200t. And the detailed calculation you can find in the Google Colab notes. Okay, this is a simple example how we do calculate the energy for the coupled inductors. And next we're going to look at the ideal transformers.